Okay, good afternoon, sir. Today I welcome our guest speaker, Professor P.M. Walker from University of Surrey for this webinar on rotating nuclei and other objects. This is the 8th webinar of our international seminar series, started in June 2024. Sir, thank you very much for accepting our invitation and giving us your precious time for this webinar. I also welcome to the participants who joined for this webinar in online and offline mode. I'm happy to share that more than 350 participants from 150 different institutions from India and abroad have been registered for this webinar. Now I will briefly introduce Professor Philip M. Walker. Professor Walker is a distinguished nuclear physicist holding his BA and MA degree from Cambridge University and a PhD from Australian National University. Professor Walker has dedicated his career to the explanation of nuclear structure physics with a particular focus on nuclear isomers. He has served various prestigious roles such as William Penny Professor of Nuclear Physics and as a CERN Associate. Professor Walker has published more than 400 research papers in numerous high-impact articles in leading scientific journals like PRL and Nature. His work has advanced our understanding of high angular momentum states and particularly isomeric states. He is also a recipient of many awards, including a Rutherford Medal and Mittner Medal. We are honored to have you, sir, for this webinar. Today he will share his deep insights on collective rotation in nuclei. Thank you very much, sir, for your precious time. Now, over to you, sir.
Yeah, well, thank you for the nice introduction. I hope you can hear me all right.
Yes, sir, we can hear you.
Yes, so you can tell from the introduction that I've been working on nuclear physics for quite a long time. And I've spent a lot of that time studying rotating nuclei in one way or another. And it's always amazed me how much you can learn about basic nuclear structure from essentially watching a nucleus spin around. And at the same time, I've been aware that rotation is also used for studying other objects. And so I've put together a talk that really takes a tour through various rotating objects, including nuclei. And I hope you will find it as interesting as I find it. There's just so many things we can find out by watching objects rotate. So this talk will, let me just, sorry, I'm not getting an advance on the screen here. There we go. So on the left, you can see the picture of a galaxy. Galaxies are something like 10 to the 16 meters across, and they rotate roughly once every 10 to the 15 seconds. So these are such large numbers, they're rather difficult to imagine. So that's one extreme of rotation that I will look at briefly. Then particularly interesting are neutron stars. These are somehow more manageable in terms of our Earth units. So a neutron star is something like 10 kilometers across, or radius, and it typically rotates with a period of about 1 second. And then when we consider atomic nuclei, certainly I'm more familiar with these objects, and they have a radius in the region of 10 to the minus 15 meters and a rotational period of something like 10 to the minus 20 seconds. So these now numbers are so small that it's quite hard to have a feeling for them. But let's start with conservation laws. And these are the bedrock of our basic physics. We're familiar with energy and momentum, and at least for a long time, it's quite slow in our education system to really focus on angular momentum. And angular momentum is just as basic as energy and linear momentum, perhaps more basic. It's conserved in magnitude and in direction. And one problem is we don't have so much familiar interaction with angular momentum, but most of us are familiar with a spinning top. And here is a picture of a spinning top, and you can't really tell that it's spinning, but when it stops spinning, it falls over. And that's because it goes to a lower energy state due to gravity. But what keeps this spinning top standing upright is that the angular momentum vector is pointing upwards, and that's a conserved quantity. Of course, it slows down slowly by friction with the atmosphere and at the point of the spinning. But there's something very fundamental there about angular momentum, and we can define various quantities associated with angular momentum, in particular a moment of inertia, which is the sum of all the mr squareds. Well, I don't want to go into the numerical details too much, but these are working out the integral of the moment of inertia is always a good exercise. And then there's the important aspect that angular momentum is quantized. And it's not, we tend to think of it that energy is quantized, but energy is only comes in packets due to the quantization of angular momentum. And the angular momentum quanta are well defined in terms of the h bar, the Planck's constant divided by 2 pi. And when in units of h bar, the objects are called bosons, named after your famous Indian physicist. And when they're in units of half h bar, they're called fermions, and named after this Italian physicist. So I won't be going into too much about these fundamental units, but angular momentum really is the most important quantity in terms of understanding energies and other properties. But let's start off with a rather simple, relatively simple system, which we can handle. That's an egg. And you can pose the question, how can you distinguish between a raw egg and a hard-boiled egg? Well, it's quite simple. If you break it open, you can see. But if you want to do it non-destructively, one thing you can do is to spin it round. And this is an experiment we can all do. It's a bit difficult to demonstrate on the internet. So I'll leave it up to you to do the experiment. But in this orientation, if you set it spinning on a table and briefly stop it and then let go, if it's a raw egg, it will resume its spinning. So, and that tells you there's a fluid inside it that is that doesn't stop instantaneously. So that's a very simple. Oh, by the way, if you do try it, don't take the egg, a raw egg, straight from the fridge. because then it's rather viscous and it tends to stop rather quickly. But the message is that by watching an egg rotate, you can tell something about what's inside it. And that's the general message of this whole talk, is that by watching physical objects of many different scales rotate, we can tell what's inside them. And for many objects, the very big and the very small, it's really the only way we can do it. We can't break open a nucleus and kind of inspect its innards, but we can watch it rotate in a sense that we'll come back to. But let's start at the very large scale, a galaxy, and you can have a feel that that galaxy is rotating just from the swirly nature of it. And if most of the mass is in the center of the galaxy, and you have balancing forces, you expect the velocity of the stars in the outer regions to fall off as 1 over the square root of the distance from the center. That's from straightforward Newtonian mechanics. But if you look at the rotational velocity, then it flattens off. It doesn't have this 1 over r behavior at any distance. And so this curve labeled luminous is roughly what you expect just from the distribution of mass as indicated by the glowing matter that you can see. This behavior this anomalous behavior was recognized almost 100 years ago. And nowadays it's interpreted as the existence of dark matter. That is, matter that we can't see, that is a long way out from the center of the galaxy. And according to this way of looking at it, there must be much more dark matter out there in the universe than there is ordinary matter that we can understand. And it's extraordinary that really this story has been developing for almost 100 years, but we still have no good idea of what dark matter is, let alone worrying about dark energy, which is another problem. But here is some of the best evidence that there is for dark matter, and it remains mysterious. So this dark matter, I would say, is revealed by rotation. Maybe fairly soon dark matter particles will be discovered at CERN or some other laboratory, some other method, but it remains one of the big puzzles of physics today. And you can wonder if, when it is worked out what dark matter is, how much else will it change about our understanding of the universe? So I said that you need to watch the rotation of the galaxy to deduce this, and we really need galaxies on their side, a bit like this one. And then if you look at the spectral lines as you sweep across the galaxy, so you focus on the little bits away from the center, then you find that there's a Doppler shift, and it goes in the opposite direction on one side compared to the other. And that's illustrated in this picture on the right, where you can see the Doppler shifted frequencies of emissions from the galaxy. And indeed, you can see that this flattens off. So there's quite a direct indication that this is not a 1 over r squared behavior of the velocity with distance. It's much more flattened off. Going down in scale a long way to pulsars. These are now understood to be neutron stars, some 10 kilometers in radius. And the first evidence was identified by a PhD student called Jocelyn Bell. And this was the data she looked at from radio telescopes, in the new radio telescopes then in 1967. And you can see little blips on here, and they look a little bit irregular, but she realized that they weren't randomly occurring. They're very regularly spaced, and even though some of them seem to be missing, the other ones occur again at very regular intervals. And this was a complete puzzle. The press at the time suggested maybe there's some intelligence out there in the universe with a highly closely reproducible pattern of emissions. But finally, the physicists understood that it was rotating neutron stars beaming out a bit like a lighthouse. And that changed a lot the view of matter out in the universe. And Jocelyn Bell is very well known for this discovery, but it was her supervisor, Anthony Hewish, who won the Nobel Prize in 1974. But the fact that she didn't win it, she's well celebrated for not being given the Nobel Prize, and continues to be a strong advocate of physics. Now, the neutron stars have so many interesting features. As I pointed out here, you're essentially watching them rotate with these little pulses every revolution. And there's one in the middle of the Crab Nebula. So you may well be aware that the Crab Nebula was observed by Chinese astronomers as a bright object in the sky in 1054. It would be wonderful to see such a thing today. And approximately where the pointer is, there's a pulsar left over from the supernova explosion of 1054. And this can be studied in some detail. Here's I think this is infrared pictures of the center of Crab Nebula. And you can see three stars in the middle, and they're shown here every millisecond, and over a period of 33 milliseconds there's a complete cycle of intensity variations, and it's this star on the lower, slightly to the right of center, which goes away and comes back again, and this is the pulsar that's rotating with a period of 33 milliseconds. It's not a simple rotation, it's a complex rotation, and so there's a lot of detail that can be extracted about what's going on in this pulsar. Another pulsar, known as the Hulse-Taylor pulsar, was discovered by a PhD student, Russell Hulse. This was the first binary pulsar discovered in 1974. He found two periods. One was 59 milliseconds, but it was modulated on a timescale of nearly 8 hours. And he realized that it was a binary pulsar. So this rotation of two stellar objects at a high rate, and he looked at the slowing down and realized this provided the first conclusive evidence of gravitational radiation to understand the slowdown of this rotating system. And he won the Nobel Prize, which he shared with his supervisor in 1993. So this was another example of rotating objects giving basic information that isn't obviously directly related to seeing inside them, revealing the basic forces of nature and radiation. And a third feature of pulsars comes from the Vela pulsar, and that's in the middle of this object, and it has what is, I consider, a rather unusual behavior. If you plot the revolutions per second as a function of days, it gradually slows down, so it's using up its energy, rotational energy, and slowing down a little bit with time, radiating out lots of its rotational energy. And then it suddenly speeds up a bit, and then it goes back to slowing down again. And this is an almost instantaneous, hard to catch glitch of the Vela pulsar. Happens every few years. One simple physical way to think of this is that there's been a shrinkage. So as the pulsar cools gradually, you can imagine that there's a crust on the pulsar and it cracks and shrinks a bit. And when it shrinks a bit, it speeds up. And this, you may feel it's obvious, but I like to think of the ballet dancer conserving angular momentum. You know, when a ballet dancer starts off with the arms stretched out and then brings her arms in above her, then she rotates more rapidly because her radius has reduced a bit from a physics point of view. So if the radius reduces a bit due to the cracking of the crust, the pulsar would speed up a little bit before it then loses its energy slowly. In fact, it appears not to be so simple, and I'm certainly not going to go into the gory details, but it looks like the pulsar has some superfluid properties, and there are superfluid vortices that get unpinned at particular points, and that's what causes the sudden speed up of the pulsar rotation. So that's another example of the watching an object spin and then learning about its internal structure from the spinning behavior. And then I will jump to nuclei, because they have a rather comparable behavior to that pulsar. If we start off a nucleus, in this case it's tungsten 170, spinning rapidly, and it gradually slows down, and then suddenly it speeds up again, all on its own, really. So just like with the pulsar, this is due to a change in the internal structure of the nucleus as it slows down, and then it gradually slows back down again. And there's another parallel that it's with pulsars, that it's due to the superfluidity of the nucleus. And the way we can view this in nuclei is that initially the rapidly rotating nucleus has broken pairs that contribute to the rotation. But as it slows down, these broken pairs rejoin up. And when we have pairs of nucleons, then they're not contributing to the overall angular momentum. So the nucleus itself has to rotate faster as the pairs join up, and then slows down again. And this can be understood as being due to the Coriolis force. So I'll say a little bit more about that. How do we view this experimentally? Then we see a gamma ray spectrum, and in this case it appears to go in the other direction. So from slow rotation up to fast rotation, seeing gamma ray emissions as a function of the gamma ray energy, and the energies increase gradually, and then suddenly there's a reduction in the energies, and this is akin to that speeding up of the rotation as it was slowing down, that one coming from the other side. So really we should start at spin 22, 20, 18, 16, then suddenly it speeds up and then slows down again. This is a paper from 1983, but the phenomenon was first discovered in 1971 by Arne Jonsson and co-workers, and they were studying a rotation of dysprosium-160, and they made this plot of the moment of inertia, which you can deduce. I should go to the next slide. There are various equations for a quantum rotor, which I don't think I need to go into at the moment, but you can deduce the moment of inertia as a function of the rate of rotation of the nucleus based on these simple formulae. And the moment of inertia, if we imagine now, we'll start at the low end and speed up the rotation gradually. The moment of inertia goes up a little bit and then suddenly it shoots up. And this discontinuity, this sudden increase in moment of inertia, is understood to be due to the rotation alignment of particular pairs of nucleons. And the rigid rotor moment of inertia can be simply calculated because you can measure the mass of the nucleus easily enough. And the moment of inertia for a sphere is 2/5 mr squared. You can allow for the small effect of the nuclear deformation. But the measured moment of inertia is well below that of a rigid rotor, and this can be understood as being due to the superfluid behavior of the nucleus, and then the sudden increase in moment of inertia is due to the breakdown in the superfluidity of the nucleus. So getting a little more up to date with the kind of information we can get experimentally, here's a spectrum for erbium-162, which is seen up to 60 units of angular momentum, and the spectrum starting from the slower rotation and going up, there are two discontinuities. The first one is understood to be due to the alignment of a pair of high J neutrons, and the second is due to the alignment of a pair of high J protons. So there's a huge amount of detail of what's going on inside the erbium-162 nucleus that you can learn from these kind of data. Conceptually, the Coriolis force has always been a bit of a stickler, a bit of a difficult one to get your head around. And so I like to think of cyclones. Of course, cyclones are rather destructive objects on the Earth, but we're more familiar with cyclones than we are with rotating nuclei. So here's a picture of a cyclone that was in 2021 over northwest India. And a cyclone is a rotation-aligned object, like a rapidly spinning nucleus has rotation-aligned nucleons. Its rotation is aligned with that of the Earth. So this is looking down on the North Pole, and here's, conceptually anyway, not very accurately, the cyclone in northern India. And it's rotating in the same sense that the Earth is rotating. And how can we view this? Well, a cyclone develops from a low pressure, and if the wind starts closer to the equator, then it has a higher velocity in the direction of east, because that's the way the Earth is carrying it. But if the wind is flowing into the low pressure region, it's flowing north, and so its velocity is kind of overtaking the Earth, because the Earth's velocity closer to the pole is lower than its velocity closer to the equator. So there's effectively a force pushing it eastwards in that direction, and then correspondingly the air flow in from the direction of the pole is flowing too slowly to keep up with the Earth, and it is deflected to the west. And so this circular pattern is set up of air flowing into the low pressure system, which makes the cyclone. And this is very related to what's happening with the breaking of pairs as the nucleus rotates. The pairs line up with the rotation, and they contribute to the angular momentum of the whole object. And this can be analysed in terms of the Coriolis force, but I'm saving you those equations and concentrating on the intuitive aspect instead. Yes, and just to note that if we have high J nucleons, or neutrons in this case, contribute the largest angular momentum, then when they're paired up, they contribute nothing to the rotation of the whole nucleus, but when they're unpaired, they can contribute up to 12 units of angular momentum, which on a nuclear scale is quite a lot. And that overcomes, from an energetics point of view, it overcomes the energy needed to break a pair of nucleons. So that was just thinking about the straight rotation of objects. But when we're dealing with, well, also with very large, but more obviously with very small, the objects that are rotating are charged. And when you rotate a charged object, you generate a magnetic field, a magnetic moment. And so if you put rotating charged objects in a magnetic field, then they line up in certain ways, and this can be used to determine the strength of the magnetism, the strength of their magnetic moment. In a classical sense, the magnetic moment mu is equal to the angular momentum I when in units of the magneton. So if you're dealing with electrons going around atoms, this would be called the Bohr magneton. And if it's nucleons going around a nucleus, it's called a nuclear magneton, because and the mass, when it's neutrons and protons in a nucleus, is the proton mass. And if it was electrons around an atom, then it would be the electron mass. So the magnetic strength in nuclei is relatively small because the mass of a proton is much bigger than the mass of an electron. But it's the same principle. In practice, the magnetic moment is usually not quite equal to the angular momentum in these units. And we talk about a G factor. And this G factor is unity if it's classical rotation. So a nucleus rotating as a whole is composed of neutrons and protons, and the neutrons are uncharged and the protons are charged. So if we're looking at the rotation of a whole nucleus, then we should expect the G factor to be equal to the ratio of the total charge to the total number of nucleons. Because this is diluted, the protons are not generating, the protons are generating the magnetism, but the neutrons aren't. So you just get this Z over A factor. And it's possible to look at how that's behavior goes. And there's a lot of different behaviors looking at different nuclei. I chose this one somewhat arbitrarily. This shows the G factor for the first 2+ state in a series of krypton isotopes. So we can view this as rotation of the krypton isotopes and expect the G factor to be Z over A, but it's, then here's the Z over A number just superimposed, turns out to be a bit less and to have some variations that's distinctly different. So some of the data quite different from Z over A. And so what we need is a more sophisticated model to understand that. And here there's comparison with IBA2 calculations, which I have no intention of going into, but if you want to follow it up, there is a reference given. But many different models, the shell model is another choice. This is a testing ground for nuclear models and how we are to understand the simple elementary rotations of nuclei. So it gives a quite different perspective compared to just looking at the gamma ray energies as I had been illustrating before. And magnetic moments can be measured in a variety of ways, but in this case, that the half-life of these 2+ states is rather short, of order 10 picoseconds. And in that time, the rotation is only a fraction of a revolution. So it's quite hard to measure this quantity, but it's what you do is illustrated here. You put gamma ray detectors at these angles, which are carefully chosen to be the most sensitive to small rotation of the nucleus during this 10 picosecond lifetime in a magnetic field. In this case, the magnetic field is supported by gadolinium, which is a ferromagnetic material. And even for a small fraction of a rotation, you can get a significant intensity change in the radiation that comes out due to this magnetic moment rotating the angular distribution of the gamma ray emissions. It's a bit easier to understand in this example, which is an isomeric state where the angular momentum is coming from a broken pair, and we can ask the question, is this broken pair a pair of neutrons or a pair of protons? And by looking at these, here's the nucleus sitting between the poles of a magnet and the pair of protons or neutrons flying around at generating the magnetic field and causing the gamma ray intensity pattern to oscillate. As time goes backwards here, sorry, that's perhaps a little confusing, but the zero time of the creation of the nucleus is on the right. And over a time of a few hundred nanoseconds, the isomer decays away and the angular distribution pattern oscillates according to the strength of the magnetic moment. And from this, we can extract the half-life, 163 nanoseconds, and the G factor that causes the oscillations is extremely close to 1. And then it needs a little bit of nuclear modeling, but this clearly is not coming from the neutrons, which are uncharged. It's a 2-proton configuration. And then other information is needed to tie down the quantum numbers of the protons in more detail. And going to smaller objects still, the neutron itself can rotate. The neutron is a fermion, spin a half particle, but you might think it's uncharged, so it won't have a magnetic moment. But it does have a magnetic moment, and I haven't even written down the magnitude of the G factor. The point I want to make here is far more simple. The fact that there's a magnetic moment of a neutron means the neutron has substructure, and we call these quarks. You need to be a particle physicist to try and observe the quarks more directly, but so far nobody's found free quarks. So we can find free neutrons and measure that they must have a substructure. So we started off at the largest scale, looking at galaxies rotating and learning about dark matter making up a large fraction of the mass of galaxies, even though we can't see the dark matter. And here we can measure the magnetic moment of neutrons and work out that there's something going on inside neutrons, difficult though it is to extract anything from them. And I put this slide in because it's topical in the sense that this month's Physics World magazine, that's the magazine of the British Institute of Physics, had on its front cover about the muon mystery. This is sometimes, maybe usually referred to as the G-2 problem. But the point is that the muon is like a heavy electron. It's clearly a charged object, but the magnetic moment isn't quite what you would calculate. Even with the most sophisticated calculations, there are problems to understand the magnetic moment of the muon. And this could be a gateway to physics beyond the standard model. This gets a bit too complicated for me, but this is a very readable article in Physics World. It's written by this guy, Alex Kajevaresi, and he's an expert, but he's written a more understandable version for the Physics World magazine to get some insight into the complex nature of what we can learn about the inner workings of the muon and how it may affect our view of the very standard model of particle physics. So really, that's all I've got to say. Some of it is very simple, some of it gets more complicated, but the general idea is that we can use rotation to learn about what's inside objects. It can reveal amazing details that we maybe didn't expect to find. But particularly when you can't see inside these objects, rotation is a unique way to find out about the physics and the fundamental behavior. So I'm very happy to discuss this further and answer questions. Left a bit of time for discussion, but thank you for your attention.
Hello. Thank you very much, sir, for your time and this wonderful talk. Now I want to invite students to ask any question or queries if they have. Sir, one student, Dilpreet Singh, want to ask you something.
Good afternoon, sir.
Hello.
Thank you for this wonderful lecture. My question is, sir, what are the current challenges faced by scientists in studying rotating nuclei?
Yes, well, that's a good question, because in fact I said rather little about rotating nuclei. I said something, but there are many aspects of rotation that are under very active investigation. One of the most intriguing is to find the symmetry associated with the tetrahedral shape. And there's a very recent paper on samarium 152 and the structure of that, giving some good evidence for tetrahedral deformation of, that's the kind of, I haven't got a picture of a tetrahedron, but there's evidence of that kind of shape being significant in nuclei and influencing the rotational structure that you can observe. The more well studied and on a similar vein is the octopole shape, which is rather closely related to the tetrahedral shape. And there's a lot of evidence for octopole behavior. Then there's chiral properties of nuclei, chiral symmetry. So there are, particularly in odd nuclei and odd mass broken pair excitations of nuclei, they can have handedness. So, you can't superimpose a right hand on a left hand. They're mirror images of each other, and so their rotations can be different, especially if there's interactions between the different states. But there's a basic chiral symmetry. Two sets of states can be identified in a number of nuclei that seem to represent the handedness of the rotation. So there must be other things you may have in mind, something I haven't mentioned.
Yeah, thank you, sir.
Sir, there is one more question from Ms. Khushbu.
So my question is, what are the potential applications of nuclear isomers?
Okay. Well, that's a different talk, really, isn't it? But potential applications of nuclear isomers, because it's very close to my interest. So there are many actual applications of nuclear isomers already. So they're used in medicine. The most widely used imaging isomer is technetium-99 isomer. They're used a lot in the Mossbauer effect. So the iron 57 isomer is quite short-lived, but it's important that it's an isomer for the Mossbauer accuracy. Very widely used then in solid-state physics. Then potential applications, there are two that come immediately to mind. One is nuclear clocks, and there's huge advances being made with the isomer thorium-229 metastable state, which is the lowest energy isomer that we know of at 8 electron volts. And there's been a number of papers in recent years published in Nature and Physical Review letters about controlling the excitation and decay of this thorium isomer in such a way as to be able to make a nuclear clock which could be far more accurate than atomic clocks. So the same principle of using the excitation, the frequency of the excitation, to define time, but the nucleus itself is far more shielded from external perturbations than atomic states. And so that looks real. I think something will be happening there. That's definitely one to watch. More speculative is whether isomers could be used as energy storage devices. In principle, they can be de-excited electromagnetically. So it's possible to imagine having a long-lived isomer storing a lot of energy, but you could release that energy by shining a laser on it or something like that. But we seem to be far from achieving control of isomers in that way. But who knows, may not be so far. Those are the things that come to mind most quickly. You may have a favorite.
Okay, thank you, sir.
Hello.
Hello.
Thank you very much, sir. There are a few more questions in chat box. If you can read it, sir, in chat box. There are a few online participants.
Okay, yes, I should look at this. Well, there's one question.
Yes, sir.
About problems with Newton's law at the cosmological level. How can we apply Newton's law based on angular momentum conservation at the cosmic level? Yes, well, this certainly is a bit beyond my knowledge base, but I do know that one way of explaining the rotation of galaxies without dark matter is to have a modified Newtonian dynamics. And the idea there is that the strength of the gravitational force may not be exactly an inverse square law. And it's possible, at least in individual galaxy cases, to model the rotation curve with that assumption that the strength of the gravitational force is not exactly inverse square. And I think there's probably quite a lot of physicists who think that's the answer to the problem, that you don't have to invent dark matter. You can explain the data that way, and the size scale over which this operates is such that we can't measure it directly on the Earth. I would be quite happy with that, except that there are quite a lot of other bits of evidence for dark matter, so it's which would not be addressed by modified Newtonian dynamics. I hope that's addressing that question.
Yes, sir. Thank you very much, sir. There is another question in chat box. If you can scroll down, sir.
Yes,
There is
I've
another
got
in chat
pulses.
box. There is another
Pulses,
question.
yeah, pulses are the remnant of massive stars exploded from the supernova. So how can you distinguish particular remnants are pulsar or from the rotation? I think I don't understand the question. I'm sorry.
I think question is somewhat misleading. So we can move to next question
Okay.
if the audience have. Yes, anyone? Any
Can
student
the
want
characters of pulsars be explained by nuclear isomers? No, I'm sorry. I wouldn't say pulsars have anything to do with nuclear isomers. I think the comparison with nuclear rotation is quite good.
Yes, sir.
In the sense that they're both related to the superfluidity of the rotating object and how breakdown in the superfluidity modifies the way that the rotation occurs. But it's an analogy, right? It's not. It's the system is too different to say it's the same process. That's all
Yes,
the
sir.
questions I can read. Yeah.
Thank you very much, sir. There is another question from Shinam. Yes, Shinam.
Good afternoon, sir. So my question is, do rotating nuclei experience any kind of friction at atomic level?
That's an interesting perspective. Is there any friction? There's no friction. So let me try and think how to interpret that. So if you have a nucleus rotating inside an atom, then the nucleus is being held there by electromagnetic forces of the electrons. So it's somehow balanced in the middle and spinning round. So that nucleus can interact with the electrons. You can have a very well-known form of de-excitation of nuclei is so-called conversion electron emission. So the energy of the nuclear rotation can be transferred to an atomic electron, which is ejected from the nucleus. So, I mean, you could refer to that as a kind of friction. It's a slowing of the nucleus by interaction with the nuclear environment. Yeah, I've not heard it called friction, but it's an interesting way to think of it.
Thank you very much, sir. Hope student will get his answer about the friction in atomic nuclei. Sir, I want to have a particular question about nuclear rotational bands. I want to know about the angular momentum generation while backbending and band crossing happened. How angular momentum pattern is different in case of backbending and band crossing?
Yes. Well, there's a lot in that, but I would start off by saying that so-called backbending, when there's rotation alignment of a particular pair of nucleons, that is a kind of band crossing. So if you view it as the fully paired superfluid nucleus changes to a broken pair, for sake of simplicity, I call it a normal fluid nucleus with a broken pair, where the broken pair contributes a lot of angular momentum, then it's possible to imagine or even identify states that are energetically unfavored, that show that where the superfluidity is maintained and the fully paired nature is maintained, that it's just not the lowest energy state. So the backbending is a kind of band crossing, but band crossing is more general because you can get swap overs of structure just because two structures have very similar energies. Two different rotational bands are rather similar in energy, but one has a higher moment of inertia than the other, and they can cross. So that's what one might call more of a chance crossing, whereas the backbending is a much more systematic phenomenon, but they're both band crossings.
Okay, thank you very much, sir. Sir, there is one more question about, it is a general question. I want to visualize the time reversed orbit, how the proton or neutron are revolving in time reversed orbit. I'm not getting the concept of time reversed and how to visualize it and how to convey such concept to the students. How
Good.
these
Yes, good question. I would say that so time reversed orbits are paired orbits, and one nucleon is going round in one direction and the other nucleon is going round in exactly the opposite direction. But another way to imagine it is the term time reversal, time reversed orbit, because if you ran the clock backwards, you would see that other orbit. So to me, time reversed orbit and paired orbit, or time reversed orbits, plural, and paired orbits, plural, are the same thing. Somehow the time reversed statement makes it seem somehow more fundamental. The difficulty with these time reversed orbits, I don't know if you share it, is that every time the pair of particles, if they're really in the same orbit, every time they go around, surely they bash into each other. This then leads to discussion of pairing, And the fact that the nucleons come into contact with each other gives extra binding, and they scatter into other states, and maybe they have to benefit from the uncertainty principle. They can scatter into higher states for a short time without violating conservation of energy. But the states they scatter into, they're still fully paired. So it's actually a hugely complicated mechanical process, having a pair of particles interacting with each other to get the extra binding and scattering into different orbits. But this, the fact that it leads to extra binding is quite remarkable. It's one of the lovely features of nuclei, let's say.
Thank you very much, sir, for your insights, and hope all the students got benefited from your talk. And now the session is closed for a discussion and open for valedictory. Thank you very much, sir.
Thank you.
Now Raman ma'am will continue the thanks valedictory session.
Thank you so much, sir. So at the end, we want to appreciate who all are involved in conducting this lecture. On behalf of Akal University, we sincerely thanks Professor Philip Walker for his insightful talk on rotating nuclei and other objects. His expertise and valuable contribution greatly enriched the discussion and deepened our understanding on how rotating objects reveal their internal structure even when we are not able to see inside them. How dark matter is realized through rotation, how internal structure of neutron is realized through its rotation. Thank you so much, Professor Walker, for such an interesting lecture. We are greatly honored. Next, we also sincerely thank our Honorable Vice Chancellor for their continuous support and encouragement in conducting this seminar series. A special thank to Professor Sukhjit Singh, Director IQAC, for his constant support and guidance throughout this event. We also extend our appreciation to the IT team for their support and seamless coordination, ensuring the smooth execution of this webinar. And most importantly, we extend our heartfelt thanks to all the participants for their enthusiastic engagement, thoughtful questions, and contributions to the discussions. And lastly, thank you all for your invaluable contribution. Thank you so much, sir. We'll hope to have such an interesting lecture again if it will align with your schedule. Thank you so much, Professor Walker. Thank you.
Thank you very much. Thank you for the interesting questions as well.
Thank you very much, sir. Sir, if you have any message to our student, very short message you can give to our students, so that they will be motivated for research. One short message from your side to our students, sir.
Well, I think physics is lots of fun, and I hope you do too.
Thank you very much, sir. Thank you.
Goodbye.